Okay, so we're in Maple and working with a worksheet that we would normally be doing in class altogether, but I'm going to just go ahead and demonstrate some of these things because they're not features that are possible in Desmos. I'll go ahead and make this available on the Moodle site, the file, in case any of you want to play with this if you happen to have Maple on your personal computers. So this particular worksheet builds up a number of commands to essentially calculate in the same fashion that we've done by hand to calculate the Taylor polynomial of any specified degree. And then it kind of puts them all together. This command that I'll be about to show you combines several pieces of code to create a little movie so that you can kind of see what happens. And the way Maple's calculator works, we're able to see a lot higher degree functions than you can see using Desmos. And so the convergence issues that we want to be thinking about are a little more evident here. So what I've already executed this command and it's created this video is working with the function e to the x. So the calculator notation for that is exp of x. And I'm asking it to compute. I've asked Maple to do the first 100 Taylor polynomials. It is going to break down at about 56 or so, the 56th degree polynomial, but you'll get a sense for what's happening. So even with Maple, there become small number issues as you choose very, very high degree polynomials. So let me go ahead and just adjust this so you can see the whole frame. And I'm just going to go ahead and first we'll look here and you can see that what is plotted is just the constant line at height 1. And then I'm going to go ahead and move to the second frame. Oops. And you can see that here I now have the tangent line as we expected. Then the third frame is the parabola that we've computed. The fourth frame is the cubic that we would compute. So I'm just going to go ahead and now hit play, and we're going to watch all of these polynomials as we increase the degree. Watch those plotted here. And so you can see as the degree is switching from even to odd, we're seeing that tail go either up or down. But what you can see is that as we play, so I'll play it one more time. As we run this, the polynomials start to match the actual curve further on a larger and larger interval. So it's hugging the curve for a longer period of, a longer portion of the x-axis here. Now you can see that things start to break down in these jagged lines here. That's not the actual polynomials, that's just numeric errors happening. And I think I said it was somewhere in the mid-50s where things start to break down. Right, okay, so actually I would say looks like right here about the 53rd degree polynomial looks okay, and we're starting to see some choppiness coming in here now. But nevertheless, you can get a sense for what these polynomials are actually doing. If we could look at them in full accuracy, you would see the same behavior that we saw up until here, right? Where as you increase the degree, going from odd degree, the 53rd frame is actually the degree 52 polynomial. So that's even, so the ends both go up. And then the 54th frame is the degree 53 polynomial, so the ends go in opposite directions, right? As I continue to increase n, those tails are flipping back and forth, and the region of the, as I said before, the curve continues. It is better and better approximated out here at the tail. Now you can't actually see, because the frame is a little too small here, what's happening out here for large x values, but it's also the case where the curve is becoming closer and closer fit for large x values as we get higher and higher degree polynomials. And it's actually the case, we'll prove this back in your handout, and when I'm in the next video, we'll prove that in fact, eventually, for any point on the x-axis, eventually these Taylor polynomials will approximate the function value e to the x for all points x. Let me show you another example of this happening. So cooking show math style again, we've got now the function sine of x, and I'm going to go ahead and run this video. I've only got this one set up from 0 to 12. Let me go ahead and just make this fatter so we can see a little more. Okay, and we'll just run this. And here you can see, again, all of the polynomials we're seeing plotted are odd degree polynomials. That's because, as we observed, the even contributions, there's no contribution from the even powers because this is an odd function here. So, so you can see a similar pattern happening, that as you increase the degree, the red is approximating the blue well for a larger and larger interval. And in fact, I could even make this, let's make this minus 10 pi up to 10 pi. And we'll go ahead and make this up to, let's try 25. Let's see what that does. We'll take a few minutes to calculate, and then we have now, so now our window is going from minus 10 pi to 10 pi. We're going to run through 25 Taylor polynomials. So here we are, and you can see that as we continue to increase the degree, we get that in fact we're covering a larger and larger, the functions are approximating sine of x on a larger and larger region of the x-axis. All right, so it turns out that if we were to make this even larger, right, so if I made this instead of 25, let's make it 35, see if this crashes. All right, so let's try this one. And right, so if we, oops, yep, there we go. Okay, so here's the numbers breaking down here. If we were able to actually see the true polynomials and not have numeric errors, we would actually see the curve matching the sine curve all the way out here. It would just continue to hug over arbitrarily large intervals. And again, we will actually prove that mathematically. The key to all happiness will be the ratio test. But before we do that, I want to show you one more video or little animation here, just to kind of bring home the point that we're going to start investigating formulaically. I think it's always helpful to have these graphical, the graphical picture in your head while we do the computation, so you see what's happening. So I've now taken the function 1 over 1 plus x. It has an asymptote at -1. And we're going to approximate it near 0. And we're going to just look, I have 20 polynomials here, or 20 degree 0 to 20 Taylor polynomials. So let's just see what happens. So if you look at this, you can see that no matter how far we seem to be going out, let's try this up to 30, oops, not 300. Okay, let's go ahead and run this one again. And we seem to be getting closer and closer to the curve, right? At least on this region here from -1 to 1, but it doesn't really look like we're ever doing any better right here past 1. And it doesn't really look like we're ever going to do very well with this portion of the curve that's off in the left-hand side of the graph. I'm going to go ahead and just for grins, let's bump this up to 40 and see. We might get some large number errors happening here, but we can always check it out and see where things break down. So you can see here that, okay, it hasn't broken down, but we're still not getting convergence. The red curves are not getting close to the blue curve out here in this region for x values larger than 1. So we're going to go ahead and investigate this phenomenon formulaically, what's happened, and the difference between this function, the functions e to the x and sine of x, where the Taylor polynomials are approximating the function. Taylor polynomials centered at 0 approximate the function at any point, versus over here, what we're seeing is that the Taylor polynomials are only a good approximation. Taylor polynomials centered at 0 are only a good approximation for this function on this small range of x values. So we will stop this video, and we'll resume on the next video where we actually investigate this formulaically.